Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this specific discussion, we're going to look at a theorem that is basically going to be a direct application of complex numbers. And perhaps we can give this one in terms of this specific representation. I hope it's going to be having the same meaning. So in a sense, we're going to see that we can look at this specific aspect of de Moivre's theorem. And this is going to be assisting us trying to evaluate the roots and, of course, powers of complex numbers. Now, de Moivre's theorem is going to be an application of the representation of complex numbers in terms of the polar form, which we had just looked at in our previous discussion. Now, it said that we can have complex numbers represented in terms of this specific representation for the real part and the complex part given as, or rather, imaginary part given as such. And from the Gandhi diagram, of course, we can be able to represent this specific aspect of x and y given as such. And as well, we have discussed that we can represent this specific, of course, aspect of the real and complex part using what we refer to as a polar coordinates. In this case, we're going to have the cosine of a function theta, which is going to represent the real part, and the imaginary part can be represented using I, the sine of an angle theta given as such. And we said that this theta is going to be representing what we refer to as the argument or the amplitude, which is going to be, of course, the angle subscribed between this specific point of origin, or the axis, which is going to be defined as a real, of course, a component of this phasor, which we have given in terms of a z. And this is going to be representing the imaginary component, which we can give in terms of this specific representation. Now, in a sense, we're going to see that this specific point, if we have it given as such, this can be represented using the various range of course, polar coordinates, which are going to be given in terms of x and y. And we have said that in this particular case, we are going to give, for an angle theta, we're going to give this x represented in terms of r, the cosine of theta, whereby we're going to see that this is specific form of r, which we have said is going to be the distance between this specific point to the stretch, which is going to be defining this magnitude of r. And therefore, we can define as well the y, of course, coordinates of this specific, of course, representation in terms of polar coordinates given in terms of the sine of theta. Now, the two are going to be forming a representation of this specific section for x and y given as such. And this is going to be, of course, a multiple of this specific distance, which we have defined in terms of r. So therefore, we are going to be using this lower part of the representation for us to have this specific, of course, complex numbers. And therefore, we can define from this specific set of general representation an aspect of z raised to the power of n, whereby n is going to constitute what we refer to as a set of real numbers. So this can be defined by having r, which is going to be the distance raised to a power of n, and therefore we are also going to have this specific, of course, real part given in terms of the cosine of n theta given as such, plus this imaginary, of course, a unit times the sine of n theta given as such. So this is going to be representing, of course, a phasor n raised to the power of a phasor z raised to the power of n. And this, from this specific representation, then therefore it's going to be giving us what we refer to as powers of a complex number, or a power of a complex number, which can be given in terms of this phasor of a z. Therefore, we are going to see that this is going to be a general representation. Now, in a similar way, we can represent what we refer to as the roots of a complex number. And this is going to be given in terms of application of our de Moivre's theorem, which we are going to state in our subsequent video in a different form. Now, I'd like us to have a representation of this specific, of course, a form of this, of course, a form of this specific power in terms of Euler's number. Now, in our previous discussion, I've basically mentioned this concept of a Euler's number that was developed by Leonhard Euler, which was given in terms of this specific representation. Now, we had said that we can give this one as a summation of n from 0 to infinity over the functions of n 1 all over n over n factorial given as such. And as we said, this is going to be defined for a function which is going to be given as the limit in the limit as n tends to infinity of a function of a 1 plus 1 all over n raised to the power of n. And this is going to be giving us a value of this e, which is equivalent to 2.718 given as such. So in a sense, I'm going to be using this specific notation in trying to represent this aspect of the powers of complex numbers. And in case we come across them, then therefore it will be appropriate for us to identify them accordingly. So we can have this specific phasor of a complex number represented in terms of e, which is Euler's number raised to the power of this, of course, imaginary unit pi. Of course, this is going to be theta, and this is going to be representing what we refer to as this component over the complex number for the real part and the imaginary part given as such. So in a sense, we're going to see that the only, of course, variable which we have not included in this specific case is a distance from this specific evaluation. And in a sense, this particular components of the real and the imaginary part, which are constituting the cosine of theta, imaginary unit, the sine of theta, are going to be represented using this specific, of course, combination of the power of, or just power of this specific Euler's number. And therefore, we can have this phase of z given in terms of this particular representation of z is equivalent to r, and then we're going to have this specific section represented by the complex number. So this implies that we can still have this specific aspect of the complex number given in terms of this particular representation, which is r e raised to the power of imaginary units, and then theta given as such. And in case we give this specific phasor of z given as z raised to the power of n as per the de Moivre's theorem, we're going to have this specific component including the, of course, this specific aspect of Euler's number given in terms of r, e, I, n, theta. And that is going to be forming what we refer to as this specific aspect of a complex number. So in this case, or if we can represent it in this specific form, we're going to have r, e, I, theta given as such. And if this one is raised to the power of n, then therefore that's going to imply that we're going to have the first factor raised to the power of n and the second factor. And this is going to be giving us rn, e, and then we're going to have the imaginary unit and n, and then therefore it's going to be theta. So n is going to be constituting a power of course, r, and of course we're going to have r raised to the power of n, and this is specific component of the exponent of I theta raised to the power of n as well. And this is going to have an implication that we can have this one given in terms of r n given as such, and this specific aspect of this, of course, number which we have given in terms of Euler's number can be given in terms of this specific representation, and therefore this is going to be given in terms of the cosine over n theta plus the imaginary unit sine over n theta. So perhaps I can give this one in terms of this specific, of course, representation because of a space. So we shall have the cosine over n theta plus I, or imaginary unit, the sine over n theta given as such. And this is going to be representing a version of this particular equation which we have said, which is going to be representing basically what we refer to as de Moivre's theorem. And we're going to come across this specific range of theorem and try to contrast a way of finding roots instead of powers, which is going to be forming our second part of this specific evaluation. Then therefore we shall look at a few examples which are going to be assisting us try to basically represent the powers, or rather the roots of complex numbers, and try to see how they are going to be different from representation of the powers using this value of n that is a set of real numbers. So kindly check our description boxes for various links of other videos. Engage us in the comment section, and also ring that notification bell for other updates in our discussion in math and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.